So yeah, I'm going to be talking about fantastic performance and where to find it. And as Jens have just pointed out, I'm Richard Warburton, CTO of Opsine.com. We're a low overhead performance profiling, continuous profiling company. And this talk's going to kind of cover, I guess, four main areas. So the first main area is, what do I actually mean by, fantastic performance and where to find it? What are the sort of parameters and motivation of this talk? Then we're going to look at some real world profiling examples. So I'm going to run a couple of kind of lightweight benchmarks on my desktop here and fix some performance problems as we're talking live through the talk. So you've seen live coding, live performance fixing is going to happen this talk, hopefully. And then we're going to look at how you take those kind of examples and apply them in the real world on a more kind of serious production system and wrap up threads in conclusion. So firstly, what do I mean by fantastic performance? Now, there's always a requirement with a conference talk to go out there and give a big, exciting talk. What is fantastic performance? But for me, fantastic performance in many ways is not performance that requires you to do crazy or esoteric things. It's about meeting your business requirements. So keeping your customers happy, keeping your infrastructure costs low if you've got a kind of a big infrastructure budget. Scaling your software out so you can deal with as many users as your business can bring in. And importantly, not having outages whilst doing it, because there's always a reliability aspect to performance. If you have very slow software, it can become indistinguishable from unreliable software. That's what I mean here by fantastic performance. That's our end goal. And also worth noting that we want to think about performance in terms of production systems, in terms of the real world outcome, not just running benchmarks on computers. Now, when trying to meet those kind of performance goals, a lot of people think about this in terms of like architectural decisions and buzzwords, going reactive, use MongoDB, it's web scale, things like that. Now, those things are great. Like I don't want to pick on or knock any particular technologies, but picking those technologies and relying on them to achieve your goals, that's not necessarily the best decision point. That's kind of an architectural decision point. What we're going to talk about in this talk is a different perspective on those kind of problems. So looking at measurement, optimization, tuning. How can we take an existing system that works and modify its code to have improved performance, not doing a huge, high risk, expensive rewrite, but just taking what we've got existing and improving it, making it better. And I'm also here to try and help you, show you that solving these problems isn't magic. It's not about going off and doing some crazy thing or saying some magic incantation to your IDE and everything will get faster. It's a simple matter of applying some basic methodology and some tooling. And that's what we're going to be talking about in this talk. Hardware is really super fast. It keeps on getting faster and faster and faster. But in order to use that hardware optimally and get the maximum performance out of it, you need to remove the bottlenecks, the sources of inefficiency in your own software stack. And often, if you do that, simple code that's properly thought out can go like a rocket. Untuned software stacks, where maybe you've got the latest buzzword, libraries, frameworks, and things in, but that haven't had that kind of tuning applied to it, often have easy, even 10x throughput increases just hidden away, waiting for you to find them. Low-hanging fruit. And being fantastic is often more about removing those problems, removing the cruft, removing the things that are holding you back, rather than doing something crazy or off the wall. So we're going to talk in this talk about profiles, about measuring and finding bottlenecks and then fixing them, and how we can use profilers to fix those problems. So next, I'm going to look at a couple of examples. So I'm going to go and code through those examples, and we're going to find some performance problems there, and we're going to fix them. So what do we need to think about here in terms of our profiling examples? Well, what we're doing is we're going to profile those examples. And what we want to find with profiling is the main consumer of a given resource. So that resource could be CPU time, like time sitting on CPU, executing instructions, going away and doing things. It could be wall clock time, so that's the time from the beginning to the end of an operation. So that might be time that we spend on CPU doing CPU bound tasks. It might also be time that we spend waiting for other systems, especially common if you've got a microservices setup where you're waiting to talk to other systems in your overall, other services in your overall system. And then of course there can be memory. Memory is quite expensive in cloud-based environments. I feel nowadays it's often something that's very difficult or can become a big cost bottleneck. So people are interested in cutting down memory consumption quite a bit as well. And the key thing about profiling is not only does it let us measure what is using a resource, but it lets us challenge our mental model, and challenge our mental model not in a kind of an argumentative internal team, people disagree way, but challenge our mental model with data. We can look at this information, we can look at this objectively gathered information, and we can say, well, maybe we thought things were working one way, but actually they're working a different way, and that's what we need to think about. Now, I'm going to go through some profiling in this talk, but we also perhaps want to think about what do we do as well as profiling. And the first thing we can measure is just basic CPU stats on our production system and understand what is using up different types of time. And I've highlighted in green here the CPU output from VM-stat, just to give you this kind of 5 categories of CPU time. Now they're rather mystically named: us, sci, id, wa, and stu. User, system, idle, wait, and steal. And those categories are about user is time spent in user space, so your application executing CPU. Sci, system, that's in kernel space. Idle, sitting around doing nothing. Wa, waiting on external I/O operations, and sti for steal. So what we're looking for are situations where, firstly, is our CPU time focusing on spending a lot of time in user space in our own system, in which case you want to profile and try and reduce CPU usage. Are we spending a lot of time in idle waiting on other systems or on I/O operations? In which case we want to do a bit more wall clock profiling. And I'll give you examples in this talk of both CPU profiling and the wall clock profiling. The example project I'm going to show you just now, I'm just putting the link in here. You can go over to GitHub, see it there, and it's a problem. It's a project with some performance problems in. So first of all, let's go and have a look at a CPU bottleneck. So I'm going to start up my application here and get it going in the background, and it is a drop wizard application, so standard Java web service that we've got going on here, and it started up there. And I'm going to look for give you a quick demo of the kind of output it might produce. We've got a demo house search script here. So that's just going to hit a local endpoint. I was born in Cardiff in Wales. So this is basically a system that's got a bunch of house price data loaded up into it. And we are going to have a look at the house price data in Wales, in Cardiff. So if I run that, we can see that we get this data back, and we get a bunch of information here. So these are all prices sorted by sale information sorted by price. So the cheapest sale is £266. It's got postcodes and address information in. And then if we go to the bottom of this JSON output, we can see the most expensive price, and we've got a search string there. So if I go back to the script we ran to get that, we were hitting that endpoint. I'm pretty print formatting it and just running it through less so you could see things, but part of the URL, it's a query string here for finding information out. Now, I've also got a house search benchmark script just to give you some load harness here, and I'm going to run it. We're only going to run 100 queries here because these queries take quite a bit of time to run initially, but you'll get the idea from seeing that as to what's going on in the system. And I'm using for that the AB Apache benchmarking tool. So that's just an open source project. We're going to hit that with a few threads on the local machine, and the first argument provided is how long it takes. Now we can see here with our different histogram of percentiles, the latency of each request that we've put onto our service that we're looking at here. And 50%, 899, basically means half of the requests took 899 milliseconds or less to complete. And the worst case was 1.2 seconds to complete. Now, let's suppose we see this problem, we see this benchmark result, and we say, that's too slow, we want to make it a little bit faster. How are we going to do that? Well, I've got a profiler that I've attached to this, which is the Option profiler here, and I can narrow down the results and I can get you some profiling data that we've got for this system in question. So I've been running this profiler whilst I was running that benchmark. It's been a very low overhead profiler, so it hasn't impacted the performance very much. And I've got the results here in terms of a flame graph. Now, the first thing I'm going to do with the flame graph is narrow down the thread group. So we're just looking at the drop wizard thread group, threads that start with the DW name. And what I've got that you can probably see in very, very small text, don't worry, I'll zoom in there in a sec, is the flame graph. And a flame graph is a visualization of profiling data for a given computer system. And each box within this flame graph is a method, represents a method within that system. And we've got a top-down flame graph. You can also get bottom-up flame graphs as well. But in the top-down flame graph, our topmost method in our system is javalang thread.run. So that's the method that calls things. And as we go down the flame graph, that's going down the call stack. So every method, every box calls the box below it. But where flame graphs become interesting is where the boxes get narrower. So the boxes here, the width of the box represents how much time a method or its children have used up in total. So what we want to look at when we see a flame graph is where the boxes get narrower, where they narrow it down, and where we get kind of lots of smaller boxes taking up space rather than just these big fat boxes that, okay, maybe their children are taking up a lot of time, but they aren't actually using how much time themselves. So let's kind of look in here and zoom into that data again, and we can see points where we get, for example, our sales query.search. We've got a get sales data method that's using up like 60% of CPU here, and read sales is within that get sales data method. Now that immediately jumps out to me as something that's really weird, right? We don't want a getter to be a method that uses up a lot of time. If a getter is appearing in your profiling data, something really weird's going on, because a getter should just be returning a field. We can see if we have a look at that get sales data method that we've got code that looks for the field, the get sales data, and tries to lazily initialize that sales data field, right? So check if it's null. If it's not null, return the sales data. Otherwise, read the sales value. Okay, well, there's something obviously wrong and obviously missing here, which is our sales data field has never been initialized. So what we want to do is take that sales data field, initialize it with the read sales method, and then return that sales data field there. Okay, so fantastic. So I'm going to restart this project now, having made that change, and I'm going to have that code recompiled and bring that service back up again, because performance troubleshooting is an iterative process, right? You want to find a problem, fix the problem, and then move on to the next problem that you see within your system. So that's come back up again. I'm going to run another quick benchmark here. Now, these are not the most scientific of benchmarks. I've not given some extra time for warm-up, for example, but we're just here to get some rough numbers. Now we can see that we've already got a 10x reduction in the 50th percentile case here. And our worst case, okay, is still pretty bad, but really we should recognize that this is just the first time, the first request we're going to hit on the service loads things up. And if I rerun these numbers, for example, we should see that that worst case request has gone away entirely. So basically, after the first request we've made the 50th percentile about 10x faster, and the worst case is faster as well. Okay, so let's come back here and take a look at the new data. So I changed the agent ID when I reran this benchmark to be Codecamp 2 rather than Codecamp 1. And we can kind of zoom in and see back where we were on the flame graph view again and see what's going on. Well, previously we had sales search and sales query.search, and it was spending loads of time calling that getter method, that get sales data method. Now that's disappeared from our flame graph. That's fantastic. So we fixed that bottleneck. But obviously when we fix a bottleneck, the bottleneck shifts and we have something else. And we can see actually the Java streams pipeline come into vision. Now, streams have a bunch of different methods here. There you can see them within our profiling data, but streams themselves aren't really the bottleneck, right? You can kind of see if I zoom out a bit, these methods are about all the same width. They aren't narrowing down. That's not the exciting bit of the flame graph. The exciting bit comes in here, lower down, where we see a contains ignore case method that takes up a bunch of time. And within that contains ignore case method, we see a bunch of two uppercase methods, which have a lot of self time. So why are we calling string.to uppercase so much? So if I go to that sales query method, so this is our query code, we stream the data and we do a filter on it to implement our query string. We've got a big contains ignore case here, and we can see the way contains ignore case is implemented is kind of a simple DOM contains ignore case, uppercase the field, uppercase the query string, and then do a contains. Fair enough. Well, a better way of doing this might be to bring in a library. So there's a nice little string utils class in the Apache Commons framework, and that's got a contains ignore case method on it. Now we might have a look at that and hope that that is a method that is going to be more optimized than the DOM case that we've just done of just doing a two uppercase and then a contains and then another two uppercase on it. So hopefully using a third-party library is going to improve the performance of our system. Okay, so let's rerun our little benchmark harness. We can see things are a bit improved. They were like 90, 95 before. We've still got our worst case hanging around. I mean, we can rerun it as well again and see if that changes things. And again, we're about the similar kind of range before. So we've got things improved. They're about, 30% better maybe than they were before. So hopefully in my mind, I think that I've fixed this string comparison related bottleneck. And let's have a look at what our profiling data tells me has happened. So I zoom back into here, and we can see sales search is still taking up a big chunk of time. The search method is still taking up a bunch of time. The stream stuff is about the same as before. So, it's calling things that are taking up time, but the Java Streams framework itself isn't the bottleneck here. And then when I get to contains ignore case, I see that there's a lot of time being taken up with the string utils contains ignore case method. Now, that doesn't mean that the code change that we've made isn't an improvement. This code here is definitely an improvement over the previous code that we had in place below. And we can see that because our benchmarking numbers have gone down. But it's still the primary bottleneck of the application. So even though it's faster, if we want to improve things, we still need to focus on this big bottleneck as being the source of our performance problem, not other things elsewhere in our app. So having used a third-party library to try and speed things up, I'm going to use another kind of key trick that we have, which is, can we use a bit of domain knowledge to simplify the problem? Now, the business requirement we have is we want to make a comparison on our input query string, our query input, as being within any of these fields within our sales data, ignoring the case. But one thing I didn't mention early on was actually those fields are already stored in our data store in uppercase format to begin with. So we can actually, using that domain knowledge, simplify the problem down entirely. We uppercase our query inputs to provide the query string and simplify things completely. We don't even need to have a contains ignore case method. We can just use the regular Java contains method and rely on the fact that the data in our data store is already in uppercase format. And even if it wasn't, we could do things like pre-process that data or add another field, for example, that loads that up on startup and use that pre-processing the data to find the uppercase equivalent. There's a bit of a trade-off there between memory consumption and straight line speed, but certainly things that we can think about. Here we've already got the data in the ideal simplified format, so that's grand. And if we rerun the benchmark now, well, we're down at 40 milliseconds. So, you know, and if we run it again, 40, and our worst case is around about 80. So we are now roughly 20 times, in fact, over 20 times, nearly 25 times faster than we were at the beginning of this benchmark run, just by doing this really, really simple task of finding the biggest problem, looking at that bottleneck, and fixing it. So I'm going to look at another performance optimization example here, blocking bottleneck type problems. So people often look at profilers and think, well, profilers are quite good at finding CPU-bound performance problems, but maybe you're in a situation where you have a lot of performance problems that aren't CPU bound. They are situations where you're waiting for external services, a database I/O. So what can a profiler offer you in those situations? Can you still apply the same methodology? The answer is yes, but you need to think about what you're measuring a little bit differently. So I've got a demo app here, and I've got this legacy bank service that is running in the background on the same machine here. And my demo application is going to do a migration of some database entries. So what am I going to do there? Well, I've got another script called merge accounts, and that is going to run in parallel a bunch of benchmark requests on the local host with different user IDs 1 to 4, pulling them in. Let me get this started. It takes a bit of a oops. Let me start my backend service up running so we can run that benchmark. So once we run this benchmark here, we are going to run this merge accounts benchmark. So that is going to hit a few situations where we try and merge in data from our legacy bank service and bring it into the new service. So, you know, what it's actually doing, you know, doesn't necessarily matter that much from a performance point of view. The interesting thing from a performance point of view is this is a situation where we aren't doing much CPU bound work. As you'll see when you look at the code in a sec, what we are doing is we are doing situations where we have a merging operation. So it took 30 seconds. There we go. We're doing a merging operation, and we are looking at an external service. So we've got an IO heavy piece of work. Now, if we just run this with CPU profiling turned on, so it's measuring CPU time, there's not anything, I mean, you can go through all of these things if you were so interested, but I can tell you from having looked through this, it's not a very interesting situation. And if you're looking at the metrics on a quiet, clean machine when you're running this benchmark, i.e. not necessarily on my desktop at the moment, because I've got a web browser running, I've got an IDE running, just things for doing this talk. If you're running on a clean, quiet benchmark machine, you'd see there wasn't much CPU being used when running this benchmark. And that is time when you want to look at a different type of profiling time from your profiling data. So not CPU time, i.e. time spent on CPU, but wall clock time, time spent from the beginning to the end of the application. Okay, so we can see our wall clock time looks very different in terms of its profile. And I'd only look at wall clock time if you're not CPU bottlenecked, by the way. But now we're not CPU bottlenecked, what's actually going on? Well, a lot of time is being spent waiting for a connection to come in. That's what this server socket channel impl.accept means. So we can kind of just ignore this and look at these situations on the left and on the right where we're actually handling requests. So I'm just going to zoom in to this flame graph. This is a very, very simple flame graph. There's a whole bunch of code here, which we don't really care about, don't need to know what it's doing, but it's basically running Jetty code, Glassfish code, Drop Wizard code. But we don't care about it because these boxes have the same width. You can just see that visually looking at the flame graph without reading the methods or anything. They've got the same width, so they're not interesting. What's interesting is this point down here where we narrow down. And we've got a method here called merge balance from legacy bank account, which kind of makes sense given that's the operation that we were running. And it is calling legacy bank proxy.get bank balance. But 75% or 74% here of the time disappears between our merge balance and our get balance operation. That's where our flame graph, you see, narrows down, narrows in. That's the exciting thing to look at within the flame graph. So let me go and have a look at that bank class a second. And we want to look at the merge balance from legacy bank account method. Now, if you've got a lot of self-time, it means that a lot of work is being done within this method normally, but not for wall clock time. We know that we're calling some other methods here, get bank balance, find safely by ID, deposit, persist, blah, 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 blah. But those methods aren't taking up much time. They're not appearing in our flame graph. What's really taking up the time here is the work we're doing. Now, we don't do any maths, we don't do any loops, we don't do any computational work. What we're waiting on, clearly, the only thing left in this method by a process of elimination is waiting on this transfer lock. And if you look at that lock, it's just a single static object. So all threads that are calling this method within this system rely on that one big lock. And I'm going to change over to what I've got a get lock method here, which gives us a per customer locking configuration. So what that means is we're going to have one lock per customer for updating their particular bank account balance. So we're still safe from a concurrency perspective of updating that customer's bank balance, but we are not going to have the global synchronization and lock contention problems that our previous code had. And I'm going to rerun my benchmark here. That the previous benchmark took, roughly 30 seconds. I'm removing the lock contention problem here, and hopefully that is going to speed things up. And it has. We're down to 15 seconds. Fantastic. So if I just go and have a look at this profiling view here and the latest run that I've just done now with the new agent ID, and zoom back in again as we did before, we can see we have an even simpler flame graph. Before, we got to one method, then we narrowed. So that was this method in here, we're doing the merge balance, that took up loads of time, that's disappeared. The child method, get bank balance, takes up as much time as this one does. Okay, fantastic. And it goes all the way down to the socket read 0 method at the bottom. So what is that method doing? Well, get bank balance is just doing an HTTP GET request on another service. So it's doing an HTTP GET, as you might see with many kind of microservices type setups. When we get to the bottom of our flame graph, let me zoom in again so you can read that clearly. We've got a socket input stream .socket read method that's taking up 100% of the time here. Our benchmark is bottlenecked on this method. What does that mean? Well, it's not CPU time bottlenecked, it's wall clock time bottlenecked on that method. It's waiting on that method. It's waiting on reading data from a socket. Or in other words, it's waiting for the external service that we were talking to respond to the HTTP GET request that we have here. And this is a really big clue. If you're looking at wall clock profiling data and you see an IO method at the bottom that's eating all the time, reading data or writing data over a socket, reading data or writing data over a file, it's what is that thing talking to? If it's a file, you need to read or write less data. If it's a socket, you need to speed up the other system. Now, if I was in a real environment, what I would do is I would go and apply the same optimization methodology that I have just done to an external service. But this is a conference talk demo, and I can't spend the entire day optimizing things for you. So what I've done there is I've just restarted that other service, and I've basically set a flag to say run faster this time. So I've only modified the external service, and I've done that based upon the profiling data from my service that tells me, look, it's a bottleneck on reading data from that other system. And if I run that, I find we're down to 0.6 seconds, so way, way faster. So we were really being bottlenecked within this system, firstly by a lock within our demo application, and we used wall clock profiling to find that lock and then fix it. And then we saw from the wall clock profiling data again that we were waiting on talking to an external service, and then we fixed the external service that was slowing us down. Cool. So that's an example of how you can use wall clock profiling to find non-CPU bottlenecked performance problems. Now, the kind of next big section of this talk is profiling the real world, because I've shown you a few examples of Java code here and how we found the problems and fixed the problems, but there's a bit of a gap that needs to be overcome, that needs to be leapt over in order to go from profiling in a demo environment on a laptop, whatever, to profiling in a real world production system. And what I do is look at a bunch of different problems that we have to overcome and how you overcome that problem. The first problem is being representative. And firstly, that means being representative in terms of the workload that you're using with your system. Okay, so I had some performance benchmarks and I was optimizing against those benchmarks on my desktop. If your benchmarks, your workload, are doing different things to what your real users are doing, then you can be optimizing the wrong part of your software system. And it's not just about hitting, say, for example, the same web pages or the same parts of the software system. It's about hitting it with the same patterns of data access, with the same caching behavior. You know, if you have a real world system that's accessing 20 different accounts and your benchmark is just hitting the same account over and over and over again, then you might find that things are being cached very effectively in your benchmark, but they aren't going to be cached as effectively in a real world system where you might be having a wider range of values than just caching. It's not just caching, it's all sorts of problems. The key point here is you need to be, if you're going to have a synthetic load test or a synthetic benchmark, it has to be as close as possible to the real world one in order to be good. The second part of representativeness is hardware. Now, in general, people don't do development on the same hardware as they run in their production systems. I talk to developers, all over Europe, and many of those people say, for example, that they are developing on a Mac, or that they are developing on some other different system or different piece of software to their production environment, their production hardware. And their production hardware is, it can often be a lot beefier, a lot more powerful than their development environment. And often the mental model in that situation is like, well, if I make it faster on my laptop, it'll be faster in production as well. Now, that's true to an extent, but often you find that these bottlenecks go in different places. If you're just looking at a pure CPU-bound bottleneck, yeah, probably true. If you're looking at something that's doing a lot more work with different threads, well, a 2 or 4 core laptop that runs less threads concurrently from a production system will have less likelihood of being bottlenecked on a lock, a big hot lock with lots of different threads contending over it, than a 64 core production server. Similarly, you might find that you've just been handed out a new laptop by IT with a brand new NVMe disk in that's going super fast, whereas production systems can often be, especially in legacy data centers, can be refreshed on a slower cadence. They can be maybe using an older SSD or an older hard disk. Even if they've got faster CPU, the ratio of their disk to CPU speed might differ. So if you have different hardware, your bottleneck can be in a different place, and you can waste time trying to solve the wrong problem. The third part of being representative is the software itself. If you have a different version of your software stack, be that operating system, JVM, anything like that, it can push your bottleneck in a different place. So many people do development on Mac OS, or they do development on Windows, and they run their production system on Linux. And the performance there in terms of the CPU scheduler and the kernel, and especially the network stack, can be very, very different. I have open source projects where I run CI on Linux and I run CI on Windows, and time again, the difference between those two things flushes out and helps me find race conditions in tests in CI and things. And it's the same thing in your production environment. The image on screen is actually a timeline of different Linux distros, because operating systems aren't really one version. They're versions that get updated over time. They have different versions there, and sometimes these versions matter a lot, especially with the Spectre and Meltdown patches. There was a May 2018 patch Tuesday update for Windows that tanked UDP network throughput by 40%. So sometimes just these regular security patches now are also a big issue. The solution to all of these representativeness problems, one solution would be to try and get the same hardware, the same software, the same workload as your production system. But a better solution, a simpler solution, is just to measure in a production environment. Real systems, real data with a real workload. And in order to do that, you need a low overhead profiler. So I'm just going to mention some open source low overhead profilers. Async profiler, honest profiler, perf, flight recorder, things like that. Those are available. They're low overhead enough for you to go into production. Our company, Optcian, also has a low overhead continuous profiler that we have very low overhead on and is continuous. So we'll talk about what that means in a little bit as well. Problem number 2, intermittent issues. So triggered by bursts of data or rarer issues, weekly, monthly, annual issues, timing issues. So things where you have performance problems, but they're not continuous problems. So you can't just look at them, attach a profiler, and see what's going on, what the bottleneck is at that point in time. They might come and go. So how are you going to use a profiler to investigate those more tricky issues? And the solution to that problem is continuous profiling. So continuous profiling means, one, always be profiling your production system. So just run it. When it's low enough overhead, you can just run profilers all the time. You'll get that data. You'll love it once you start doing it. Retain that historical data, so keep it stored somewhere, keep it indexed. And that means you can compare data. You can look at different versions of your software. You can look at data for these weird one-off things that happen once a month. You can slice and dice to just those points in your system where you had those performance problems. Problem 3, infrequently used code. So this is perhaps a trickier one to kind of understand. So traditional profiling basically says, have a benchmark. That benchmark should dominate the workload, and then we can see what the thing is, the bottleneck for that benchmark. Production systems tend to be a little bit different from that. They often have code that is very valuable, but isn't necessarily used all the time. And you want that valuable code to be fast, but if it's infrequent, how do you look at that prod data and see from the prod profiling data what's going on? Classic example of this is customer signups. Now, you want your sign-up process flow for customers to be smooth. You don't want to lose customers at that stage, and you want it to be fast as well. You don't want to have people sitting around and waiting. They will just browse to your competitors' websites. But customer signups are often not that much of the actual traffic on a website. They're a critical point, but often it's kind of using the website rather than the sign-up process. And that's where querying your profiling data comes in. Slicing and dicing that historical profiling data, being able to filter it. So for example, saying, look, this is the method from my sign-up process. Show me all the profiling data that goes to this method. This is the method that hits this URL. Show me all the profiling data for that URL. If you profile continuously, over time, you build up a statistically significant number of samples for looking at the profiling data for even one-off, very, very intermittent or very infrequently used code bases. Just by looking at that data over a week, something like that, rather than looking at 5 minutes of the data. And then by querying, you focus on the profiling samples that are relevant to, for example, your sign-up flow. That solves that problem very effectively. The kind of problems 4 and 5 are like the access and the scale type problems. So, and these are the last real problems that we need to fix here. And those problems of access and scale are that certain organizations have access restrictions. So you can't necessarily just SSH into a production server and run your profiler on that server. You might need to think about having some security barriers in there. So how do you give access to people who need it, but restrict access as well? And then you also have that Chinese wall element, especially in financial firms where you have a legal separation between operators and developers. And then there's the scale issue. How do you make this kind of profiling work on not just one machine, but on a cluster of 100 nodes? And this is where I think you need to think about decoupling the profiler from the visualization. So thinking about services and systems to take those JVM agents, put that data into a common aggregation service, and then being able to view that on a web report. That's what we do at Opsian, for example. And that means that you can have those agents in your system, you can get the data out of them, and you can understand what they're doing without having to do things like SSH into individual servers one by one in order to get that data back. Okay, so let's look at the conclusion of this talk. So firstly, a big shout out, big thanks to loads of people who've done loads of fantastic work over the years on profiling in Java and in the JVM. So flame graphs that I showed earlier in the talk, the idea was come up with by Brendan Gregg. People like Andrew Pangin, Jeremy Manson, Johannes Rudolph have worked on low overhead profilers, and Nitsan Wakart as well. And then also the Mission Control and Solaris Studio teams, like great work by lots of people who have been improving the overhead and the quality of profiling in the Java JVM ecosystem. Quick recap of our benefits of profiling production. So firstly, improving the responsiveness and reliability of our system by fixing those bottlenecks. That gives us happier users. Cheaper infrastructure by making our software more efficient, needing less servers to run, less infrastructure to run in general. Happier accountants. Always good to keep the accountants happy, I think. And then scalability. Once you've removed these bottlenecks, you can get your system using more and more users concurrently. So people whose goals are growth, like senior management, like VCs, and hopefully, if you're a software developer and you like the company you work for, that's you as well who wants to scale out, that we can solve that problem with profiling as well. More technical takeaways, kind of key tricks for looking at profiling data. You want to have an understanding of where your bottleneck is. If you're on CPU, if you're CPU bottlenecked, look at a CPU time profile. If you're not CPU bottlenecked, don't look at a CPU time profile, look at a wall clock profile, okay? That'll tell you a different view of your system. When you're looking at flame graph visualizations, you want to find where they narrow down. That's where you get self-time within your flame graph. That's the exciting bit of the flame graph, where it narrows down. And finally, the kind of trick which I think is super useful to know if you're using flame graphs for profiling production systems, when you've got tail nodes in wall clock profiles that have high self-time and they're calling socket code or IO code, that's not the system in question that needs to be optimized. That's talking to an external service. Could be another microservice, could be a database, for example, if a stack trace is going through the database call. Or it could be reading files. And if it's reading files, you want to write or read less data, optimize your file layout rather than optimizing your CPU code necessarily. So that's kind of other things to think about when profiling. What I showed today is the data-driven optimization of performance problems. So that is take a bottleneck, find the biggest problem, fix it, and iterate, and do that iterative approach, because that is the best way to solve performance problems, I think so. Understanding performance isn't really a matter of like taming a magical beast. It's something that we can approach scientifically, methodically. We can identify specifically where problems occur using things like metrics and profiling and through systematic measurement. It's not just an approach that works in a lab environment or on a desktop. You can use it in real world. In the fact, it works better with real production systems because you get the real code and the real data. And as long as you're able to investigate that problem with the right kind of methodology and tooling, then you can find and fix those problems. And that's the end of the talk. As I mentioned, if you're interested in taking a look at our profile or an option, you can just go to our website. And if there are any questions, I'm very happy to answer them now.
Always, we always have questions. But first of all, congrats for the presentation, for the very insightful, walkthrough. I very much enjoyed how you methodically, as you mentioned, methodically analyzed everything. So it's like a brilliant approach, I would say. My first question would be related to a recent case study, real world case study that you would have maybe to better understand how do you emerge in an organization? How do you discuss with the engineers? How much do you walk the talk, or how get people to embrace tools like yours?
Yeah. How do people embrace continuous profiling? So I think it's always easier to embrace this kind of stuff when you've got like a sort of like a modern DevOps approach, right? Where you can deploy things into software, where you can iterate on them easily and quickly. And if you're in that world, it's great, right? You can just put an agent like we have onto a production system that talks back to a SaaS server, and then you can look at the data right away and tell you what's going on there. And then that gives you a great basis for a range of different people to look at those dashboards, share that common objective view of what their software system is doing. So that could be software developers, it could be people looking at more the ops server side of things. They can all see that. If you've got a more traditional deployment cycle, things can be a bit trickier. That might be a case where you need to have people inside the organization talk to each other more, get comfortable, try something out in a development environment or in a QA environment first before going to production. But that's already a matter of what the organization does itself in terms of how fast it can get things into prod in general.
Yeah, thank you. I was reading your blog about how you did it for TransferWise.
Yeah.
You can share a bit about that, because first it struck me, what's elusive performance? Elusive performance
problems that did they have? Yeah, so they had an interesting case actually, which they've used our tooling for a while, but the kind of case that and we can't talk about everything there, but the case we talked about in our blog post was a situation where basically they'd already used another APM tool, and what their other APM tool was doing was it was measuring a Java servlet application cycle effectively. So it was measuring when you get your start of your request and when you get the end of your request, and looking at what's going on inside those systems. And so they had a problem with like one of the endpoints in their system, and it was intermittently slow. Like people would just get multi-second annoying pauses that their users were saying, and they would look at the HTTP requests from their APM system, and that would be like, oh, don't worry guys, everything's fine, it's all going really nice and fast, there's no problem. They'd be like, well, we know it's slow because we can use it and feel it's slow, but the tooling is telling us something different. And the problem was essentially that they actually had a service that was doing some kind of class path scanning and reloading like an HTTP resource periodically, right? So it was a simple configuration issue. And if you put a profiler at it, that's instantly easy to spot, because you see like we've got a load of time that we're doing class loading, scanning through the URL class loader, all sorts of stuff like that. And you're like, why is that the biggest bottleneck? This should be an HTTP service. It shouldn't be doing that. And then you can go back to your bottleneck. But if you're just looking at the HTTP request response cycle, you won't see that kind of problem at all, because you'll be looking like over here at the problems over there. So that's kind of an interesting example where profilers are more like hypothesis-free, bias-free compared to some other tools out there.
Yeah, exactly. Those are, I think, one of the toughest situations where, yeah, you don't measure the whole spectrum, and then you think you see that you're doing everything right, but then you have users or other system complaining that things are going slow, and you cannot pinpoint what's happening.
Exactly.
All right, Richard. Well, thanks a lot for joining us. It's been awesome as always. And yeah, we're looking forward to the next time.